For more information, please visit SGMAK Associates website.
Hi, here is another audio file on complex numbers. I've put a title part 1. There will be more material coming. I think there are 10 problems here. I'll walk you through those problems, and as again, any questions, just get back to us. So first problem is find the solution to the following equation. If z is a complex number, z squared plus z complement equals 0. So you're solving for x and y. So z is represented as x plus iy, real axis and imaginary axis. Complement of z is x minus iy, is the image of the point x and iy on the x-axis. So what we have here is z squared plus z complement equals 0. That comes out to be x squared minus y squared plus x plus I times 2xy minus y equals 0. Then, always the approach is you equate real and imaginary parts separately. On the right hand side, you have 0. So the real part, x squared minus y squared plus x is 0. And the imaginary part, 2xy minus y equals 0. Now, imaginary part gives you two values of y, 0 or 1/2. And then for y equal to 0, you get a value of x as 0 or minus 1. So that's one pair of solution. Two solutions there, right? And then x equal to half, you get y as plus minus square root of 3 over 2. So the solutions are x0, y0, x minus 1, y0. With x 1/2, y is square root of 3 over 2, and x 1/2, y is minus square root of 3 over 2. So there are 4 solutions. Let's look at the next. So it says complex number z is x plus iy, and z raised to the power 1/3 is a minus ib. If those relations hold, then we can show that x over a minus y over b is k times a squared minus b squared. So if you can get to that form, what's the value of k? So what do you do? Z raised to the power 1/3 is a minus ib. So you take the cube on both sides. Z is a minus ib raised to the power 3i is the imaginary number, square root of minus 1. So z is a cube minus 3ab squared plus I times b cube minus 3a squared b. So x is the real part and y is the imaginary part. And then if you get x over a minus y over b, comes out to be 4 times a square minus b squared. So going back to the original problem, the value of k is 4. Okay, let's look at the manipulation that you have. Find the imaginary cube roots of unity. So if imaginary cube root is 1, omega is the imaginary cube root, so omega cube is 1. If we factorize, omega minus 1 multiplied by omega squared plus omega plus 1 equals 0. So the possible values are omega equal 1, but cannot be 1 because omega is imaginary. So we got to solve for 1 plus omega squared equals 0. And then we get two roots, 1/2 times minus 1 plus square root of 3i, and 1/2 of minus 1 minus square root of 3i. So those are the possible roots. 1 is the square of the other one. So roots are 1, omega, and omega squared. 1 is not a root. Roots are 1/2 minus 1 plus square root of 3i and 1/2 minus 1 minus square root of 3i. Problem. If a plus ib times c plus id equal capital A plus I times capital B, then show that a minus ib multiplied by c minus id equals capital A minus I times capital B. Again, you take what's given, then equate real and imaginary parts, separate out the value of a and b. So from the first equation we get AC minus BD plus I times AD plus BC equals A plus IB. So if you equate the real part, capital A is AC minus BD, capital B is AD plus BC. So now if you do A minus IB, that can be written as A minus IB times C minus ID. It's just a simple algebraic manipulation. The next problem. Find the square root of A square minus A minus 2IA. It can be written as A minus I square. So the square root of that expression is plus minus A minus R. Very simple problem. Find the modulus and amplitude of a complex number. If a complex number in the form of A plus IB, the modulus is square root of A square plus B square, and the amplitude, the angle theta is given by tan inverse B over A. So in this case, Z is given, we simplify it. As you can see here, we want to make the denominator whole number. We want to get rid of the imaginary part from the denominator. So we get 1 minus 10 plus I minus 25I squared divided by 26. I squared is minus 1. So this expression comes out to be 24 plus 10I over 26, or you can write it as 12 over 13 plus I times 5 over 13. So A is 12 over 13, B is 5 over 13. So the modulus is square root of 12 over 13 squared plus 5 over 13 squared, and which happens to be 1, and the amplitude is tan inverse 5 over 12, tan inverse B over A. Let's look at if Z be a complex number and Z plus 1 divided by Z minus I is purely imaginary, then find the locus of Z. Show that its locus is lies in a circle with center minus 1/2 minus 1 plus I and radius 1 over square root of 2. So first let's simplify this expression, Z plus 1 divided by Z minus I. So substituting Z equal X plus IY, and if you can see this simplification, again you want to get rid of imaginary part in the denominator. So we get x squared plus y squared plus x minus y divided by x squared plus y minus 1 whole square plus I times an expression x minus I plus 1 divided by x squared plus y minus 1 whole square. Now this expression contains only the imaginary parts. The real part is 0. So, and the real part, if you look at the real part, the denominator is positive. So the numerator has to be 0. So we have x squared plus y squared plus x minus y is 0. That can be written as x plus 1/2 square plus y minus 1/2 square equal 1/2. So that's a circle with center minus 1/2 and 1/2 and radius 1 over square root of 2. Okay. So Z lies on a circle with center minus 1/2 plus 1/2 I, or minus 1/2 into 1/2 into minus 1 plus I. We're taking the center as minus 1/2 and 1/2. We're writing in the form of x plus IY, and the radius is 1 over square root of 2. Let's look at the next problem. Given this x equal 1 plus 2I, find the value of x cubed minus 5x squared plus 11x. So x is 1 plus 2I, so x minus 1 is 2I, squaring both sides, we get x squared minus 2x plus 1 equal minus 4, or x squared minus 2x plus 5 equals 0. Then we factorize x cubed minus 5x squared plus 11x. We break it into what's known, x times x squared minus 2x plus 5, and then what you're left with is minus 3x squared plus 6x. the expression within the bracket is 0. Now if you look at 6x minus 3x squared and if you substitute x equals 1 plus 2i, we get the numerical value equal 15. So the expression x cubed minus 5x squared plus 11x is 15. Okay. X is given as expression, repeating expression, square root of minus 3 plus, square root of minus 3 plus, again a square root of minus 3, infinite series. So simple way to write it, as you can see the repeating pattern, you can write x is square root of minus 3 plus x. Squaring both sides, you get x squared minus x plus 3 equals 0. So if you solve for x quadratic with some imaginary roots, the roots are 1/2 of 1 plus square root of 11 times I, or 1/2 of 1 minus square root of 11 of I. Looking at the value of the expression, only valid value that you get is x as 1/2 of 1 plus square root of 11 times I. The last problem of this group of 10, if omega be the imaginary cube roots of unity, not omega, if two imaginary cube roots of unity be alpha and beta, so alpha is omega and beta is omega square, then find the value of alpha raised to the power 4 plus beta raised to the power 4 plus alpha raised to the power minus 1 times beta raised to the power minus 1. So alpha is omega and beta is omega square, the cube root of unity. So alpha raised to the power 4 is omega raised to the power 4, which is omega cube times omega, which is omega, and beta 4 will be omega square raised to the power 4, which is omega raised to the power 6 times omega square, which is omega square. So this expression becomes 1 plus omega square, which is 0. Okay. Go through this problem. They are fairly simple, based on equating imaginary and real parts separately, because they belong to two separate axes, independent axes, and some problems are based on cube roots of unity. Okay, I'll come back with more problems. Okay, bye. Hi, we are posting materials online. If you have any doubts or any questions regarding the materials posted, feel free to get in touch with us through email. Provide your name, address, school name, your contact information. We also welcome if you provide comments so that things can be improved upon. We also appreciate if you provide any feedback. Okay, so let us know what do you think about the material posted. Okay, bye now.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.